Good morning. This is 20th lecture of A-level chemistry lecture series. In the 19th lecture, we discussed about chemistry of nitrogen. And there we talked about the position of nitrogen in the periodic table. And then we talked about bonding of nitrogen and how strong bond it is that we discussed. And then later on, we took some compounds of nitrogen, specifically nitrogen oxides and nitric acids. And then we say ammonia. Ammonia is a very important compound. And we also discussed a little bit of its industrial preparation. And then we were talking about how to prepare ammonia in the laboratory. That was the summary of the 19th lecture. Now we go for the 20th lecture, and there we show you how we prepare ammonia in the laboratory. We take a ammonium salt. Okay, but excuse me, I took the pointer. We take ammonium salt, in this case ammonium chloride, and then a base. There it is calcium hydroxide, and then if we react, we get ammonia gas. And that is how we prepare in the laboratory. This is the apparatus of the laboratory preparation of ammonia gas. Here is the reactant, and then we heat it, and there we dry the ammonia gas with calcium oxide in it, and then we collect the ammonia gas in the collecting tube. You know the ammonia is a base, and therefore a damp litmus paper turns damp red litmus paper turns into blue. This is an acid-base reaction. Ammonium ion acting as an acid and hydroxyl ion acting as a base. And this is what we call acid-base reaction. Well, then we go for a little bit more about nitrogen chemistry. And there we will see that nitrogen oxides are very useful, but as well as it becomes a primary pollutant. I'll talk about right now this. In the last 19th lecture, we show how in the atmosphere nitrogen reacts. Nitrogen very unreactive, inert element, but with thunderstorms, that means a very high temperature in the atmospheric oxygen, it reacts into nitrogen oxides. Nitrogen has very many different oxides, and here we show this one is NOx. We call it NOx in the upper atmosphere. Well, similar reaction we get in a car engine. When we have in the engine a mixture of air and fuel, we compress it and then ignite it with the spark. Under this high pressure and high temperature, nitrogen form nitrogen oxides. These oxides then comes through the exhaust fumes, and that nitrogen oxide pollutes our atmosphere. And from there, we get pollution, acid rain, and photochemical smoke. Then now we have to talk about what is acid rain. Well, this nitrogen oxide, the primary pollutant, get further oxidized, and then with water, little bit of water, I show the reaction here, and then it gets aqueous nitric acid. This aqueous nitric acid in the atmosphere with the droplets of cloud, and then tiny drop of water comes down and forms acid rain. And acid rain is a very pollutant one. We have seen also that it is not only nitric acid, sulfuric acid is also in the acid rain. So how sulfuric acid comes into pollutant? SOx, we call it SOx, sulfur oxide, SOx, sulfur fluoride. NOx, causing acid rain directly can also, this NOx can also catalyze to form sulfur dioxide into sulfur trioxide, you see. And then with rainwater, it becomes sulfuric, dilute sulfuric acid. So this is dilute sulfuric is how this reaction occurs. Sulfur dioxide, nitrogen oxide, goes sulfur trioxide, and then sulfur trioxide with water gives us aqueous sulfuric acid. This aqueous sulfuric acid and aqueous nitric acid form the acid rain. Okay, now you might ask, what is acid rain? Well, rain which has a pH less than 5.4, we call it acid rain. But in our, we have seen acid rain as low as pH 1 to 2. There's a very strong acid rain, and this damages our atmosphere severely. So I take the next slide to show you photochemical smoke, how it occurs, photochemical smoke. This nitrogen oxide, we have been saying that it is the dangerous pollutant in the atmosphere because they react to make other pollutants. For example, sulfur oxide. These other pollutants form called secondary pollutants. So in fact, nitrogen oxides we get directly, so it is a primary pollutant, and due to nitrogen oxide, other pollutants we are getting this, we call it secondary pollutants. So exhaust fumes from car also have volatile organic compounds, VOCs. Why these are formed? Due to unburned hydrogen carbons from fuel, and they're oxidized products. These VOCs can react in the sunlight with oxides of nitrogen to make peroxyacetyl nitrate. See, we call it PEN, PEN. It is CH3, CO3, NO2. Sunlight provides the energy needed to start the reaction of the atmosphere. So we call them photochemical reactions. The smoke is smoke. The photochemical smoke hangs over in many cities of the world in certain weather conditions. The word smoke is derived from the two words smoke and fog. Well, we have been talking also about ozone layer depletion in our last lectures. Here we have to also minimize the NOx from the car exhaust. Therefore, nowadays people our companies are fitting catalytic converters to reduce the pollutants from the motor vehicles. And if it's nitrogen oxide, then it reacts with carbon monoxide, and then carbon dioxide is not healthier than us, and we get nitrogen gas. This is what it is. Well, next slide, what I do, I show you that how many lectures we have been already delivered, and we discussed that. You see, it's part Pearson Edexcel AS level chemistry and Cambridge International AS level chemistry. Their AS level chemistry syllabus is this. So for core inorganic chemistry and physical chemistry for Edexcel AS level, we have touched all this 1, 2, 3, 4, 5, and 5. Also, this all we have touched already, and therefore now we have to start with both organic and physical chemistry also. If we go here, Cambridge International, we could say that with atomic structure, atoms, molecules, stoichiometry, chemical bonding, states of matter. At these 4 we have touched here. In the inorganic syllabus, we have touched all this by this 19th lecture and the 20th lecture today. Yes. You can see that in Cambridge International AS syllabus, there are chemical energetics. The 5 is chemical energetics. If we come here, we can see in Edexcel, it is topic 8, energetics. So from next lecture, we take this topic, energetics. Here it is called chemical energetics, but here it's called energetics. So it's the same thing, same content. So now we are going to this chapter, enthalpy changes. You know, we have chemical reactions, and if we energetically classify this chemical reaction, we call exothermic reaction, another we call endothermic reaction. What is exothermic reaction? Heat transfer, heat energy transfer to the surroundings are described as exothermic reaction. If heat energy comes from the surrounding or absorbs from the surroundings, we call it endothermic reaction. So here is an exothermic example of an exothermic. We take magnesium metal and sulfuric acid, we get magnesium sulfate aqueous and hydrogen gas. This is what is an exothermic reaction. If I explain a little bit more, if the above reaction is done in the test tube, the energy release is transferred to the surrounding. That means in the solvent, energy release transferred to the solvent, air in the test tube, and also we keep a test in the test tube a thermometer, the energy release there, it transferred this to the surroundings. This we call surroundings. There are many other examples of chemical reaction with an exothermic condition. A few important ones we can call combustion of any fuels. This is exothermic. Oxidation of any carbohydrates. This is exothermics. Reaction of water with quicklime, exothermic. I just named few of them. So, you know, many reactions are there in a chemical world. So we can classify those as one exothermic, another one as endothermic. Here, you see this another reaction we show the following reaction. It's the reaction with citric acid and sodium hydrogen carbonate. It absorbs the heat energy from the solvent, the test tube, and the air. And that one is an endothermic reaction, you see. So, and some other examples of endothermic reaction is all thermal decomposition reactions are endothermic. Photosynthesis is endothermic. Ammonium salt dissolves in the water. These are endothermic reactions. Okay, now we take this enthalpy change and enthalpy profile diagram to explain this endothermic and exothermic reaction. Okay, mind this, the surrounding we have been talking, it should be a constant temperature, a constant concentration, so-called enthalpy change. What is it? The energy exchange between chemical reaction and its surroundings at constant pressure is called the enthalpy change. Enthalpy, total energy is associated with the materials and react. Symbol of enthalpy is H. Mind it, we cannot measure enthalpy directly, but we can measure change in enthalpy when heat energy is exchanged to the surroundings. So change in enthalpy, delta is the Greek word delta means any change in any quantity, Therefore, delta H means the change in enthalpy change. So what is enthalpy change? Delta H is equal to enthalpy of products minus enthalpy of reactants. That is what we call delta H, enthalpy change. Okay, we can explain this also with the enthalpy profile diagram below. We take one of these here, you see, one of these here, reaction path of a diagram of combustion of methane. We say that combustion of methane, you remember fuel, combustion of fuel is an exothermic one. So what we get there is methane, and we are giving energy to it and then oxidized it. And then this is the profile of the enthalpy profile. here is the reactant, and here we have the product. And the change in enthalpy is this. This is the reactant part. This is also reactant part, and that is the product. So this one is the enthalpy change of this particular reaction. And if you say that exothermic enthalpy change is a negative value. So there we can see that delta H is minus 890.3 kilojoules per mole. If we take another reaction showing the enthalpy change, here is the calcium carbonate solid. Yes, so this is the reactant, and this is the product. This is the product. So enthalpy change for this one is from here to here. So it is plus. So this plus 572 kilojoules per mole is the enthalpy change for this reaction, and that is what we call the endothermic reaction. So this is a profile of exothermic reaction, and this is a profile of endothermic reaction to show the enthalpy change and enthalpy profile diagrams. Okay, next what we take, I would say it's a summary. For an exothermic reaction, heat is lost from the reactants, okay, and the value of delta H is negative. So remember, for exothermic reaction, heat is lost from the reactants, and the value will be negative, and delta H will be negative. For an endothermic reaction, heat is gained by the reactants. Heat is gained by the reactants, and the value of the delta H is positive. I showed in the reaction that, do you remember, when drawing reaction pathway diagram, remember that the activation energy arrow should start at the level of the reactants and end at the highest point of the energy hump. This is the highest point of energy. So, and then when drawing this energy, we said make sure the arrow points downwards for an exothermic reaction and upwards for an endothermic reaction. Okay, arrow upwards for an endothermic reaction and downwards for an exothermic reaction. We have to remember this. Okay, then we not only said that you say that with temperature and other condition, we can also change the enthalpy. So therefore, we must have to talk about standard enthalpy changes. So what is standard enthalpy changes? We say that enthalpy change is shown by delta H. And this is the symbol, a symbol standard state of enthalpy changes. This symbol, standard state. And this is what is the temperature we also make. So that is what is the temperature. And then this is the R. R means type of reaction. Whether it is a reaction or a combustion or a formation, this is what is so. And H is the enthalpy. In the next slide, we will talk a little bit more about it. Yeah, the value of the enthalpy change changes vary with change in temperature, pressure, or concentration. So we have to carefully specify what is the what state of enthalpy change we are talking about. Therefore, condition has to be carefully specified for the standard enthalpy changes. The standard enthalpy conditions are a pressure of about 100 kilopascal, which is approximately atmospheric pressure at sea level. The temperature we are talking is 25 degrees Celsius, that means 298 degree K. And then substance in their standard state, most stable state, at 100 kilopascals and 208 Kelvin. That is what is the standard enthalpy change. Solution with the concentration, if it is a solution, the concentration to be 1 mole per dm cube. So I talked about it, this one, you remember. And then enthalpy change for formation, we do it like this. You see, we are not mentioning temperature here. But we say that standard enthalpy temperature is this, and therefore this is just omitted because it is constant. So standard enthalpy change, there's a enthalpy change for formation, for combustion, for neutralization, or if we get this sign, it is enthalpy change for the reaction. Well, we have to continue this enthalpy changes with some problem, and I will also take 2 or 3 problems and solutions. For this lecture, we have completed the 20th lecture now, and hopefully the 21st lecture will continue with enthalpy changes. Thank you very much for your attention. Thank you.